December 19, 1942. Leningrad Front, Soviet Union. A massive steel shape emerged from the winter fog near a small railway station outside the village of Sinyavino. Soviet reconnaissance units watching German positions reported something they had never seen before. A tank larger than anything previously encountered, armor that appeared impossibly thick, a gun that dwarfed the weapons mounted on Soviet 34s. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. The Germans called it the Tiger. German propaganda promised it would change the course of the war. Within 18 months, American engineers would capture one intact and discover why Germany was losing, despite possessing what appeared to be the world's most powerful tank. The Tiger I heavy tank represented Germany's answer to a fundamental problem that emerged during the invasion of the Soviet Union in the summer of 1941. German Panzer III and Panzer IV tanks, adequate against French and British armour in 1940, proved dangerously inadequate against Soviet 34 and KV-1 tanks. The 34 combined sloped armour, a powerful 76mm gun, and mechanical reliability into a design that shocked German forces. The KV-1 heavy tank mounted even thicker armour that German anti-tank guns struggled to penetrate at combat ranges. In response, the German Army Weapons Office issued specifications in May 1941 for a new heavy tank, mounting the 88mm anti-aircraft gun, the same weapon that had proven devastatingly effective against Allied armour in North Africa when used in a ground role. The design competition between Henschel and Porsche resulted in Henschel's design being selected in April 1942. Production began in August 1942 at the Henschel factory in Kassel. The specifications were genuinely impressive and represented significant advances in armoured vehicle design. Combat weight of 57 metric tons made the Tiger I the heaviest tank in widespread service during 1943. This massive weight was approximately twice that of American Sherman tanks weighing 30 tons and significantly heavier than Soviet 34 tanks weighing 32 tons. Frontal armour of 100mm mounted vertically provided protection that no Allied tank gun could reliably penetrate through 1943. Side armour of 80mm gave the Tiger protection against most anti-tank weapons from angles where lighter tanks would be vulnerable. This comprehensive armour protection created a tank that could survive hits that would destroy any Allied tank. The main armament, an 88mm KWK-36 gun, represented the most powerful tank-mounted weapon in service when the Tiger entered production. The designation KWK indicated Kampfwagenkanone, meaning fighting vehicle cannon. This was an adaptation of the legendary 88mm flak gun that had terrorized Allied forces in North Africa. Muzzle velocity of 810 meters per second with standard armor-piercing ammunition provided penetration capability exceeding any Allied tank gun through 1944. At 1,000 meters range, the gun could penetrate 120 millimeters of armor, sufficient to destroy any Allied tank frontally with a single well-placed shot. At 2,000 meters, penetration remained adequate to defeat Sherman tanks through frontal armor, while Sherman guns at the same range could not reliably penetrate Tiger frontal armor. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This enormous advantage in effective engagement range gave Tigers the capability to destroy enemy tanks before coming under effective return fire. German tank doctrine emphasized this principle. Engage at maximum range, where German optical superiority and gun performance provided decisive advantages. Destroy the enemy before he could close to ranges where numerical superiority might prevail. The Maybach HL 2-10P45 engine represented sophisticated German automotive engineering applied to military requirements. This water-cooled 12-cylinder gasoline engine, mounted in a 60-degree V configuration, displaced 21 litres and produced 650 metric horsepower at 3,000 revolutions per minute. Normal operational output was between 550 and 600 horsepower at lower engine speeds to reduce wear and extend engine life under field conditions. This power output provided a power-to-weight ratio of 11.4 horsepower per ton. By comparison, the Soviet 34 achieved 15.6 horsepower per ton, while the American Sherman achieved 13.3 horsepower per ton. The Tiger was significantly less mobile than the medium tanks it was designed to dominate. The engine consumed high-octane gasoline, requiring a minimum of 74 octane for reliable operation. Germany struggled to produce adequate quantities of high-octane fuel from synthetic fuel plants as the war progressed. The Tiger's fuel appetite would become a critical weakness as German fuel production collapsed under Allied bombing. The Maybach transmission represented the critical weakness that would ultimately define the Tiger's operational reality. This semi-automatic transmission provided 8 forward speeds and 4 reverse speeds through a complex system of pre-selector gears and hydraulic actuation. The design was theoretically advanced, allowing the driver to pre-select the next gear and then engage it with a simple movement of the main shift lever. However, the transmission was designed for a tank weighing approximately 40 tons. The Tiger's actual combat weight of 57 tons exceeded design parameters by over 40%. This fundamental mismatch between design specification and operational reality created cascading mechanical problems that no amount of field modification could fully resolve. The transmission suffered from chronic overheating during extended operations. The hydraulic fluid that actuated the gear changes would break down under high temperatures, leading to erratic shifting and eventual complete failure. Oil seals designed for lower pressures failed prematurely under the higher loads imposed by the Tiger's excessive weight. Gear teeth, adequate for 40 tons, wore rapidly when subjected to the torque required to move 57 tons across variable terrain. Maximum road speed of 38 km per hour provided adequate tactical mobility when the transmission functioned properly. Cross-country speed of approximately 20 km per hour under favorable conditions gave the Tiger mobility comparable to other heavy tanks when mechanical reliability permitted sustained movement. Operational range of 195 km on roads assumed optimal conditions with proper maintenance and careful fuel management. Cross-country range of approximately 110 km reflected the dramatically increased fuel consumption of off-road movement through difficult terrain. Fuel capacity of 540 litres required frequent refueling during sustained operations, creating logistics demands that German supply systems increasingly struggled to meet as the war progressed. Road fuel consumption of approximately 2.8 litres per kilometre meant that a 100-kilometre road march consumed over half the fuel capacity. Cross-country consumption could exceed 5 litres per kilometre, meaning that extended cross-country movement consumed the entire fuel load, in just over 100 kilometres. These specifications made the Tiger theoretically superior to any Allied tank in service through mid-1944. The thick armour could defeat hits from American 75mm guns at all practical combat ranges. The powerful 88mm gun could destroy Sherman and 34 tanks at ranges exceeding 2,000 meters. British and American tank commanders who encountered Tigers in Tunisia and Italy described the experience as terrifying. German propaganda celebrated the Tiger as proof of German technical superiority. Newsreels showed Tigers crushing obstacles, destroying targets at long range, and shrugging off hits that would have destroyed lesser tanks. The Tiger became a symbol of German military power, a weapon that would restore German dominance and compensate for increasing Allied numerical advantages. The reality revealed itself gradually through combat reports, intelligence assessments, and ultimately through the systematic examination of captured vehicles. The first Tigers deployed to combat in August 1942 on the Leningrad front. The initial deployment of 4 Tigers to the 502nd Heavy Tank Battalion near Leningrad represented Germany's attempt to demonstrate the new weapons capabilities against Soviet forces. The deployment was premature. The Tigers had not undergone adequate durability testing. Crews lacked proper training on the complex new vehicles. Maintenance personnel did not fully understand the sophisticated transmission system. The result was predictable disaster. Within weeks, all 4 Tigers were lost, not to Soviet fire, but to mechanical breakdown and crew abandonment. German official reports documented the failures with bureaucratic precision that revealed the depth of the problem. Transmission failures occurred first. The Maybach Olvar transmission, inadequately tested before deployment, failed under the stress of combat operations in muddy terrain. One Tiger broke down during its first combat mission after traveling less than 15 kilometers. The transmission overheated, hydraulic fluid broke down, and the tank became immobilized. The crew, unable to repair the complex system under field conditions, abandoned the vehicle after attempting demolition. A second Tiger suffered steering mechanism failure that left it unable to maneuver. The steering system, which used controlled braking of individual tracks to turn the vehicle, depended on the transmission functioning properly. When the transmission failed, steering became impossible. The tank could only move in straight lines, making it useless for combat operations. The third Tiger experienced final drive failure. The final drives, which transferred power from the transmission to the drive sprockets that moved the tracks, were inadequately designed for the Tiger's weight. Under the stress of turning in soft ground, the final drive gears stripped. The tank lost power to one track and could not move. The fourth Tiger was recovered after mechanical failure and transported back to Germany for examination. German engineers studying the returned vehicle identified multiple design flaws that would plague Tiger production throughout the war. The transmission required fundamental redesign. The cooling system needed improvement. The final drives needed strengthening, but production was already underway. Hitler demanded increasing numbers of Tigers to counter growing Allied strength. Fixing the fundamental design problems would have required halting production for months, an unacceptable delay. Instead, German engineers implemented minor modifications, while the core problems remained unresolved. The pattern established at Leningrad repeated across every theatre where Tigers deployed. Operational availability rates averaged between 50 and 70% throughout the war. This meant that a Tiger battalion, nominally equipped with 45 tanks, could expect approximately 30 tanks actually operational on any given day. The remaining 15 tanks were undergoing maintenance, awaiting spare parts, or disabled awaiting recovery. This availability rate made sustained offensive operations extremely difficult because operational strength declined throughout any extended operation, as mechanical failures accumulated faster than repairs could be completed. German commanders learned to factor mechanical attrition into operational planning. A Tiger company beginning an operation with 14 operational tanks might have only 8 operational after 3 days of sustained movement and combat. The transmission remained the critical failure point throughout the Tiger's service life. A French technical report compiled after the war, based on examination of Tigers captured in Normandy, stated that the Tiger's transmission had an average service life of approximately 800 kilometers under optimal conditions. Under combat conditions with frequent maneuvering, the service life dropped to as little as 300 kilometers. For comparison, the Sherman's transmission regularly exceeded 5,000 kilometers between major overhauls. Soviet 34 transmissions, while crude compared to German designs, were simple enough that field maintenance units could rebuild them using basic tools. The Tiger's transmission required specialized equipment, trained technicians, and parts that were increasingly unavailable as Allied bombing disrupted German supply chains. The metallurgical quality of Tiger components declined throughout the war as Germany lost access to critical alloying elements. Molybdenum, which increases steel's resistance to heat and fatigue, became increasingly scarce after Allied bombing of Norwegian mines. Nickel, essential for high-quality armor plate, was in critically short supply by 1944. German engineers compensated by adjusting steel formulations, but the resulting materials were inferior to earlier production. Late-war Tigers had noticeably poorer material quality than early production vehicles. Armor plates that should have been uniformly hard showed soft spots where heat treatment was inadequate. Transmission gears that should have lasted hundreds of hours failed after dozens. The production statistics reveal Germany's strategic error. Germany produced 1,347 Tiger I tanks between August 1942 and August 1944. Production peaked at 104 units in April 1944. These numbers sound impressive until compared with Allied production. The United States produced 49,324 Sherman tanks between February 1942 and July 1945. The Soviet Union produced over 57,034 tanks during the same period. For every Tiger Germany produced, the Allies produced over 75 medium tanks. The cost differential was equally stark. A Tiger cost 650,000 Reichsmarks to produce, compared to 103,000 Reichsmarks for a Panzer IV medium tank. Germany could have produced 6 Panzer IVs for the cost of one Tiger. Those 6 Panzer IVs, while individually inferior to the Tiger, would have provided far greater cumulative combat power because they would actually be available for combat rather than awaiting maintenance. Production efficiency favored Allied designs overwhelmingly. A Sherman required approximately 10,000 man-hours to produce in established factories operating at peak efficiency. A Tiger required approximately 300,000 man-hours, 30 times more labor for each unit. This massive difference in production efficiency meant that Germany devoted disproportionate industrial resources to produce relatively small numbers of sophisticated vehicles. American factories used advanced production techniques including extensive subassembly, standardized components across variants, and progressive assembly methods that minimized skilled labor requirements. German factories relied more heavily on skilled craftsmen to fit components that were less precisely standardized, increasing production time and costs dramatically. The operational consequences of these production differentials compounded over time. American armored divisions that suffered tank losses in combat received replacement vehicles within weeks. Crews knew that destroyed tanks would be replaced, reducing psychological stress and encouraging aggressive tactics. German heavy tank battalions that suffered Tiger losses waited months for replacements, if they received any at all. By late 1944, many Tiger units operated at less than 50% authorized strength, not from combat losses alone, but from inability to replace losses at rates matching attrition. Tigers destroyed in combat often could not be recovered because German forces lacked adequate heavy recovery vehicles. A disabled Tiger weighing 57 tons required specialized recovery equipment that was rarely available at the front. The Panzer Tiger, a recovery vehicle based on the Tiger chassis, was produced in very limited numbers. Only 3 were built, completely inadequate for the number of Tiger battalions in service. Standard recovery vehicles could not move a 57-ton tank. The result was that disabled Tigers were frequently abandoned and destroyed by their crews to prevent capture. The maintenance burden imposed by the Tiger consumed resources Germany could ill afford. Each Tiger battalion required specialized recovery vehicles, mobile workshops, and stocks of spare parts that dwarfed the logistics footprint of a Panzer IV battalion. A typical Tiger battalion required approximately 200 trucks dedicated to maintenance and supply. Those trucks, consuming fuel and requiring their own maintenance, represented a massive logistics burden. The fuel consumption differential compounded the problem exponentially. A Tiger company of 14 tanks conducting a 100-kilometer road march consumed approximately 4,000 liters of gasoline. A comparable company of Panzer IV tanks consumed approximately 2,000 liters for the same march. The Tiger required twice as much fuel to accomplish the same tactical movement. By late 1944, Germany produced approximately 6 million tons of synthetic fuel annually, barely 1/10 of American petroleum production. The Tiger's appetite for scarce fuel made it a strategic liability even when it functioned mechanically. German forces frequently had operational Tigers sitting immobilized because no fuel was available to move them. The psychological impact on German forces of their supposedly superior equipment's mechanical fragility emerges clearly from captured documents and post-war interviews. German tank crews learned through bitter experience that their Tigers were unreliable. The knowledge that their vehicle might break down at any moment, stranding them deep in enemy territory, created caution that undermined aggressive tactics. Commanders hesitated to commit Tigers to bold maneuvers because they feared mechanical failure more than enemy fire. A Tiger Company commander in Normandy reported in July 1944 that he could not execute orders for a counterattack because only 6 of his 14 Tigers were operational. The other 8 were undergoing transmission repairs, awaiting spare parts, or disabled with cooling system failures. This tactical paralysis, imposed by mechanical unreliability, contributed to German defensive failures during the final year of the war. The Tigers' debut in North Africa provided early warning signs that German leadership chose to ignore. The 501st Heavy Tank Battalion arrived in Tunisia in November 1942 with 20 Tigers. These represented Germany's first deployment of heavy tanks to face Western Allied forces. The initial engagements were tactically successful. Tigers destroyed numerous American and British tanks in battles around Tiburba and Mejez el Bab. Allied tank crews reported that their guns could not penetrate Tiger frontal armor. Intelligence reports circulated through Allied commands warning that Germany had deployed an invincible new tank. But behind the tactical successes, the mechanical problems were mounting. By December 1942, availability rates had dropped below 60%. Transmissions were failing. Cooling systems were inadequate for the North African heat. Tracks were breaking under the strain of the Tiger's weight. Maintenance units struggled to keep Tigers operational despite intensive efforts. The most comprehensive examination of Tiger mechanical reliability came from an unexpected source. On April 21, 1943, British forces advancing in Tunisia captured Tiger 131 intact near Jebel Jaffa. The tank had been abandoned by its crew after becoming immobilized in soft ground. German recovery units, overwhelmed by other disabled vehicles and under Allied pressure, could not retrieve it before British forces secured the area. This single captured Tiger became the intelligence windfall that Allied forces desperately needed. British technical intelligence teams from the Royal Armoured Corps immediately secured the vehicle and began preliminary examination. Within days, the Tiger was transported to a secure testing facility where engineers from Britain, the United States, and Canada would spend months conducting the most thorough analysis of German armour technology attempted to that point in the war. The examination team included mechanical engineers, metallurgists, armour specialists, and weapons experts. They had orders to document everything about the Tiger, every specification, every design, feature, every strength, and, critically, every weakness. The resulting reports would fill hundreds of pages and fundamentally reshape Allied understanding of German armoured capabilities. The exterior examination revealed immediately why Allied tank guns struggled against the Tiger. Frontal armour measured 100 mm thick, mounted vertically rather than sloped. While vertical mounting was less efficient than sloped armour, the sheer thickness provided protection that exceeded anything Allied tanks mounted. Side armour of 80 mm was thicker than the frontal armour of most Allied tanks. Engineers conducted penetration tests using captured German ammunition and Allied tank guns. The results confirmed frontline reports. The American 75 mm M3 gun, standard armament on most Shermans, could not penetrate Tiger frontal armour at any practical combat range. Even at point-blank range under 100 meters, the 75 mm rounds failed to punch through 100 mm of face-hardened armour plate. The British 17-pounder gun, the most powerful Allied anti-tank weapon in service, it could penetrate Tiger frontal armour at ranges under 1,000 meters, using armour-piercing, discarding sabot ammunition. But this ammunition was scarce, and the 17-pounder was not yet widely deployed. Most British tanks still mounted less powerful guns. Soviet testing of captured Tigers revealed similar results. The F-34 76 mm gun mounted on the 34 could not reliably penetrate Tiger frontal armour even at close range. Soviet tank crews learned to target the Tiger's side and rear armour, which was more vulnerable, or to aim for specific weak points like the driver's vision port. The Tiger's 88 mm gun impressed Allied engineers with its power and precision. Test firings demonstrated that the gun could penetrate 120 millimeters of armor at 1,000 meters range. This meant the Tiger could destroy any Allied tank from distances where return fire was impossible. The optical sights, manufactured by Zeiss, were acknowledged as superior to anything the Allies possessed. But then the engineers began examining the transmission, and understanding dawned. The Maybach Olvar transmission appeared sophisticated on paper. 8 forward speeds and 4 reverse speeds provided excellent theoretical flexibility. The semi-automatic gear selection should have made the driver's job easier compared to manual transmissions. In practice, the system was a maintenance nightmare. British engineers disassembled the transmission completely, documenting each component. What they found shocked them. The transmission contained over 200 separate parts, many requiring precise adjustment and careful maintenance. The hydraulic control system used fluid-filled chambers and complex valve assemblies to actuate gear changes. Any contamination of hydraulic fluid would cause erratic operation. The gear sets themselves showed design compromises that explained the chronic failures German units reported. The gear teeth were adequate for a 40-ton vehicle, but marginally sufficient for a 57-ton tank. Under sustained high-load operation, the teeth wore rapidly. Once wear exceeded critical limits, the teeth would strip completely, causing catastrophic transmission failure. British engineers calculated that the Tiger's transmission operated continuously at approximately 85% of its design load capacity during normal operations. Any extended period of high-stress operation, such as climbing hills, traversing soft ground, or executing rapid maneuvers, would push the transmission beyond its design limits. Failure was inevitable. The only question was when. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The cooling system proved equally problematic. Engineers noted that the radiator capacity was barely adequate for the engine's heat output under normal conditions. During high-load operations, the engine generated more heat than the cooling system could dissipate. Coolant temperatures would rise, creating pressure in the cooling system. Gaskets and seals designed for normal pressures would fail, causing coolant leaks. Once coolant levels dropped, engine temperatures would spike, risking catastrophic engine failure. British test drivers operated the captured Tiger for approximately 160 kilometers during evaluation trials. Even this limited operation revealed mechanical problems. The transmission overheated during extended running. Shifting became progressively more difficult as hydraulic fluid temperatures rose. On one test run, the transmission failed completely after approximately 100 kilometers of mixed terrain operation. British mechanics disassembled the failed transmission and documented the damage in detailed technical reports. The clutch plates showed excessive wear. Several gear teeth had stripped. The hydraulic control valves were damaged from overheating. British engineers concluded that the Tiger's transmission could not be considered reliable for sustained operations under combat conditions. The final drives, which transferred power from the transmission to the track drive sprockets, showed similar design inadequacies. British engineers calculated that the final drive gears were operating at loads approaching their maximum design capacity. The gear teeth showed wear patterns consistent with chronic overloading. Metallurgical analysis revealed that the steel used in the final drives was of good quality in this early production example, but the design margins were insufficient. British technical reports concluded that the Tiger represented impressive engineering in many respects, but suffered from fundamental design flaws that rendered it unsuitable for sustained mobile operations. The armor and gun were excellent. The mobility and mechanical reliability were inadequate. For a defensive weapon positioned in prepared positions, the Tiger was formidable. For an offensive weapon required to advance hundreds of kilometers through variable terrain, the Tiger was a liability. These findings were compiled into intelligence reports distributed through Allied commands. Tank crews received simplified bulletins highlighting Tiger vulnerabilities and recommended engagement tactics. The psychological impact was significant. Allied tankers learned that while the Tiger was dangerous, it was not invincible. More importantly, they learned that Tigers frequently broke down, offering opportunities for engagement under favorable conditions. The Americans conducted their own exhaustive examination of captured Tigers. The first relatively intact Tiger captured by American forces came from Tunisia in May 1943. As Axis forces collapsed, multiple disabled Tigers were recovered from battlefields. Several were in condition suitable for detailed examination. American ordnance teams shipped the best-preserved example to the Aberdeen Proving Ground in Maryland for comprehensive testing. Aberdeen had been testing captured enemy equipment since early in the war. German tanks, guns, and vehicles of all types arrived regularly for evaluation. The Tiger represented the most significant prize to date. American engineers subjected the Tiger to the same systematic analysis British teams had conducted. They measured, photographed, tested, and documented every aspect of the vehicle. Their conclusions largely confirmed British findings, but added important details about specific mechanical weaknesses. American test drivers operated the Tiger for extended periods, pushing the vehicle harder than British tests had done. They wanted to understand not just how the Tiger performed under controlled conditions, but how it would behave under the stress of sustained combat operations. The results were damning. During a 60-kilometer cross-country test run simulating combat conditions, the Tiger suffered multiple mechanical problems. The transmission overheated after 30 kilometers. Oil pressure in the hydraulic system became erratic. Shifting became difficult and required excessive force. After 50 kilometers, the transmission failed completely. Disassembly revealed that clutch plates had burned, and several gear teeth had stripped. American engineers calculated that at this failure rate, the average Tiger could be expected to suffer a major transmission failure every 300 to 400 kilometers of mixed terrain operation. For sustained offensive operations requiring advances of hundreds of kilometers, this meant that mechanical attrition would reduce Tiger strength by 50% or more before the enemy was even engaged. The engine cooling system failed during high-temperature testing. American engineers operated the Tiger in conditions simulating summer temperatures in southern Europe. The cooling system could not maintain safe operating temperatures during sustained high-load operation. Engine temperatures exceeded safe limits. Coolant boiled. Pressure built up in the cooling system until gaskets failed. American metallurgists examined the armor plate using techniques not available to field units. They cut samples from various locations on the captured Tiger and subjected them to microscopic examination and hardness testing. The armor quality was generally excellent in this early production example. The face hardening process had been properly executed. The backing layers showed appropriate ductility to prevent brittle fracture. However, American engineers noted that the welding quality was variable. Some welds showed excellent penetration and proper heat treatment. Others showed defects including porosity and inadequate penetration. Under battlefield stress, these defective welds could crack, potentially compromising armor integrity. Later examination of Tigers captured in 1944 would reveal that weld quality deteriorated significantly as German production accelerated and skilled welders became scarce. The track system impressed American engineers with its sophistication, but concerned them with its complexity. The interleaved road wheel design, featuring overlapping wheels rather than conventional bogies, provided excellent weight distribution and superior ride quality. The Tiger could traverse rough terrain more smoothly than most tanks, but maintenance requirements for the interleaved wheels were prohibitive. Changing an outer road wheel required approximately 30 minutes with proper tools. Changing an inner road wheel required removing multiple outer wheels first, a process that could consume 4 to 6 hours even with experienced maintenance crews. In winter conditions, mud freezing between the overlapping wheels could immobilize the tank completely until temperatures rose enough to melt the ice. American engineers concluded that while the interleaved suspension provided theoretical advantages, the maintenance burden made it unsuitable for American operational requirements. American tank doctrine emphasized reliability and ease of maintenance. A suspension system that could immobilize a tank for hours during routine maintenance was unacceptable, regardless of its performance benefits. The fuel consumption figures measured during American testing confirmed German reports. The Tiger consumed approximately 2.8 litres per kilometre on roads under optimal conditions. Cross-country consumption exceeded 4 litres per kilometre. With a fuel capacity of 540 litres, this meant operational range was severely limited. American engineers calculated logistics requirements for a Tiger battalion and compared them with requirements for a Sherman battalion. The Tiger battalion required approximately twice as many fuel trucks to support the same tactical movement. The Tiger battalion required 3 times as many maintenance personnel. The Tiger battalion required 4 times as many spare parts by weight. These logistics multipliers made the Tiger extraordinarily expensive to operate even before considering production costs. The American technical intelligence reports concluded that the Tiger represented a powerful weapon system compromised by mechanical unreliability and excessive logistics demands. The reports noted that Germany's decision to produce Tigers rather than larger numbers of more reliable medium tanks represented a strategic error that Allied forces should exploit. The way to defeat Tigers was not to engage them frontally in gunnery duels, but to force them to maneuver extensively, stressing their mechanical systems until inevitable breakdowns occurred. These intelligence findings shaped American tactical doctrine throughout, in 1944 and 1945. Tank destroyer doctrine emphasized using mobility to flank Tigers, engaging vulnerable side armor rather than challenging frontal armor. Infantry anti-tank tactics stressed close assault from concealed positions, attacking Tigers from directions where armor was thinner. Artillery doctrine incorporated anti-tank missions, using indirect fire to destroy or disable Tigers that had stopped for any reason. The Battle of Normandy in June through August 1944 provided extensive operational data on Tiger reliability under sustained combat conditions. German forces deployed approximately 120 Tigers to Normandy across 4 heavy tank battalions. The 501st Heavy SS Panzer Battalion, 502nd Heavy Panzer Battalion, 503rd Heavy Panzer Battalion, and elements of Panzer Lehr Division all fielded Tigers. The operational reality in Normandy confirmed every weakness that testing had revealed. Tigers broke down constantly. Availability rates dropped below 50% during sustained operations. Battalions that began operations with 40 operational Tigers might have only 20 operational after 1 week of combat and movement. Allied air superiority forced Tigers to move primarily at night to avoid fighter-bomber attacks. Night movement increased mechanical stress and complicated maintenance. Tigers that broke down during night movements often could not be recovered before daylight brought renewed air attacks. Disabled Tigers became targets for artillery and airstrikes. Many Tigers were destroyed while awaiting recovery rather than during direct combat engagement. The 501st Heavy SS Panzer Battalion arrived in Normandy with 45 Tigers in June 1944. By the end of July, only 15 remained operational. Of the 30 Tigers lost, approximately 20 were abandoned due to mechanical failure or fuel exhaustion, rather than combat damage. German records documented the breakdown in detail. Transmission failures accounted for approximately 40% of mechanical losses. Engine problems, including overheating and cooling system failure, accounted for approximately 30%. Final drive and suspension failures accounted for most remaining losses. The 502nd Heavy Panzer Battalion reported similar experiences. The battalion began operations near Villers-Bocage with 38 Tigers. Within 2 weeks, operational strength had dropped to 18 tanks. The battalion commander reported that mechanical reliability was the primary factor limiting combat effectiveness. Tigers that functioned mechanically could dominate local engagements, but the inability to maintain adequate operational strength prevented the battalion from achieving strategic objectives. British forces captured multiple Tigers in Normandy in various states of repair. Technical intelligence teams examined each captured vehicle, documenting mechanical condition and failure modes. The pattern was consistent across all examples. Transmissions showed excessive wear. Final drives showed damage from overloading. Cooling systems showed evidence of chronic overheating. Track systems showed damage from the Tiger's excessive weight. One particularly well-documented capture occurred near Villers-Bocage on June 13, 1944. Tiger No. 250 from the 1st Company, 501st Heavy SS Panzer Battalion, was abandoned by its crew after suffering transmission failure during combat operations. British forces secured the vehicle before German recovery units could retrieve it. British engineers examining Tiger 250 found that the transmission had failed catastrophically after approximately 150 kilometers of operation. The tank had been delivered to the battalion in May 1944, brand new from the factory. Within 1 month of frontline service, the transmission was completely destroyed. British technical reports noted that this failure timeline matched predictions based on earlier testing of captured Tigers. The metallurgical analysis of this late production Tiger revealed significant quality deterioration compared to earlier examples. The armor plate showed variable hardness, suggesting inconsistent heat treatment. The welding quality was notably poor, with numerous defects visible to the naked eye. The steel used in transmission components showed lower alloy content than earlier production Tigers, confirming that Germany's access to critical alloying elements had deteriorated significantly. Soviet forces on the Eastern Front compiled extensive operational data on Tiger performance through examination of destroyed and captured vehicles. Soviet technical intelligence operated with the same systematic thoroughness as Western Allied efforts. Every captured German vehicle was examined, documented, and tested, when possible. Soviet reports confirmed that the Tiger's mechanical reliability was poor compared to Soviet tanks. The 34, while less sophisticated than the Tiger, achieved operational availability rates above 75% throughout the war. Soviet commanders could rely on their tanks to function when needed. German commanders commanding Tigers could not make the same assumption. Soviet testing at the Kubinka Proving Ground near Moscow subjected captured Tigers to extreme conditions, deliberately designed to stress mechanical systems. Soviet engineers wanted to understand failure modes and establish reliability limits. They drove Tigers until they broke, then documented exactly what failed and why. One Soviet test series involved operating a captured Tiger continuously at high engine power to determine cooling system limits. The test lasted approximately 90 minutes before coolant temperatures reached critical levels. Pressure in the cooling system exceeded design limits. Gaskets began failing. Coolant leaked from multiple locations. The engine seized when coolant levels dropped too low for adequate cooling. Soviet engineers concluded that the Tiger's cooling system was marginally adequate for normal operations, but inadequate for sustained high-intensity combat operations. This finding explained why Tigers frequently broke down during extended engagements or long-distance movements requiring sustained high-power output. Another Soviet test series examined final drive durability under combat maneuvering conditions. Soviet engineers operated the Tiger through a series of high-stress maneuvers, including rapid acceleration, emergency braking, and pivot turns. After approximately 50 kilometers of this abuse, the final drive failed. Gear teeth stripped. The Tiger lost power to one track and could not maneuver. Soviet engineers calculated that under combat conditions requiring frequent maneuvering, the Tiger's final drives could be expected to fail after 200 to 300 kilometers. For offensive operations requiring advances of hundreds of kilometers, this meant mechanical attrition would be severe. Soviet commanders learned to pursue retreating Tiger units aggressively, knowing that extended movement would cause German mechanical losses, exceeding combat losses. The production timeline for Tigers revealed the strategic error in German planning. Hitler personally intervened in Tiger development multiple times, demanding increased armor protection and more powerful armament, while simultaneously demanding accelerated production. These contradictory requirements created exactly the problems that materialized in combat. The Tiger was rushed into production before adequate testing could identify and resolve mechanical weaknesses. Normal vehicle development includes extensive durability testing, where prototypes operate for thousands of kilometers under varied conditions to identify failure points before mass production begins. The Tiger program, compressed by Hitler's demands, abbreviated these crucial testing phases. Early production Tigers were essentially developmental prototypes being delivered to combat units. Design modifications were implemented continuously as problems emerged. Tigers delivered in August 1942 had significantly different components than Tigers delivered in August 1943. This lack of standardization complicated logistics and maintenance. Spare parts for early Tigers did not fit late Tigers. Maintenance procedures varied between production batches. German tank crews became frustrated with the constant mechanical problems. Post-war interviews with Tiger commanders reveal deep ambivalence about their vehicles. They praised the armor and gun, which undeniably gave them advantages in direct combat. They cursed the mechanical unreliability that left them stranded far more often than enemy fire. One Tiger company commander who fought in Normandy described his experience in a post-war interview. He stated that his greatest fear was not American tanks or tank destroyers, but mechanical failure. He knew that if his Tiger broke down during an advance, recovery was unlikely. Allied air superiority meant that disabled tanks sitting in the open would be destroyed by fighter bombers before recovery vehicles could reach them. Every kilometer traveled was a gamble that the transmission would hold together just a little longer. Tank commanders learned to nurse their Tigers, avoiding aggressive maneuvering whenever possible to reduce mechanical stress. This caution directly contradicted German armored doctrine, which emphasized aggressive action and rapid exploitation of tactical success. The Tiger's mechanical fragility created tactical paralysis that undermined German operational planning. The maintenance burden consumed resources Germany increasingly could not afford. Each Tiger battalion required approximately 250 maintenance personnel, including specialized transmission mechanics, engine technicians, and track specialists. These skilled technicians were in desperately short supply by 1944. Tiger battalions routinely operated with maintenance sections at 60% strength or less, further reducing operational availability. Spare parts were chronically scarce. Transmissions, the most common failure item, were complex assemblies requiring weeks to manufacture. By late 1944, spare transmission production could not keep pace with field failures. Tigers sat immobilized for weeks or months, awaiting replacement transmissions that never arrived. The strategic implications became clear through mathematical analysis of production and operational data. Germany produced approximately 1,300 Tigers at enormous cost in labor, materials, and industrial capacity. These Tigers achieved average operational availability of approximately 60%. This meant that Germany's investment produced the equivalent of approximately 800 reliable tanks. The resources consumed by Tiger production could have produced approximately 8,000 Panzer IV medium tanks, while individually inferior to Tigers, 8,000 Panzer IVs would have provided overwhelmingly greater combat power because they would actually be available for combat. The Panzer IV was mechanically reliable, logistically sustainable, and adequate for combat against most Allied armor. Germany's decision to produce small numbers of sophisticated Tigers rather than large numbers of reliable medium tanks represented exactly the type of strategic error that ensured defeat in industrial warfare. The pattern repeated across every category of German military equipment: sophisticated designs that could not be produced in adequate quantities or maintained under field conditions, versus Allied designs that prioritized reliability and producibility over individual performance. The human cost of German over-engineering extended beyond mechanics to doctrine and training. Tiger crews required months of specialized training to operate and maintain their complex vehicles. This training took time Germany increasingly could not afford. By late 1944, Tiger units received replacement crews with inadequate training. These poorly trained crews made mistakes that caused additional mechanical damage, further reducing operational availability. Allied crews, by contrast, could be trained to basic proficiency on Shermans and 34s in weeks. The mechanical simplicity of Allied designs meant that crews needed less sophisticated technical knowledge. Battlefield losses could be replaced quickly with adequately trained personnel. German losses accumulated because replacement crews were unavailable or inadequately trained. The legacy of Allied intelligence work examining captured Tigers shaped post-war American tank development for decades. The principle that reliability matters more than raw performance became foundational to American military vehicle design. Every major American tank developed after World War II incorporated lessons learned from systematic analysis of German over-engineering. The M46 Patton tank entering service in 1949 emphasized mechanical reliability as a primary design requirement. The transmission was conservatively designed with substantial strength margins. The cooling system was oversized to prevent overheating under combat conditions. Maintenance access was prioritized over compact packaging. These design choices reflected direct lessons from Tiger analysis. The M48 and M60 tanks continued this emphasis on reliability and maintainability. American designers rejected sophisticated solutions that increased complexity. They favored proven technology over advanced designs that might fail under field conditions. This conservative philosophy produced tanks that were perhaps less impressive on paper than Soviet designs, but that actually worked when needed. Preparing and narrating this type of story took us long efforts and hard work. So if you are enjoying the story, please consider subscribing to our channel. If you like this video, please subscribe to my channel.